Professor, this is an perturbative approach.
Yes, yes, yes.
And your results are like with confidence with experiments?
Yes, yes, for QCD, yes, yes. We see that, yes, but yeah, basically there are very few possibilities to go beyond perturbation theory. But for QCD, you can conclude, for instance, the mass of a proton, and you get it to about 3% correct in first principles. So okay, I will give this as a motivation, yes, yes. And, there's not really an alternative to it.
The resistance issue confining the study with simulations.
Yeah, well, as we know, it is a crossover, and strictly speaking, not a phase transition, and this is also a reason why it is not very precisely localized. It depends a little bit on the, let's say, autoparameter or the quantity that you look at, but you can establish it between 150 and 170 MeV, depending on the quantity you consider. As long as they are at zero chemical potential, this works quite well. If you also want to introduce a finite baryon density, then we have a problem. So we'll discuss that. Then we have a severe conceptual problem with the simulation. But as long as it's zero density but finite temperature, this is something which is doable in principle straightforward. Oh, thanks a lot.
All right.
Thanks a lot. Yes.
Well, let me just introduce you.
Okay, yes, please.
It's an honor to us to have Professor Wolfgang Wittenholz among us. Professor Wittenholz is a noted friend of us here at CBPF. He stayed for 2 years, Wolfgang. 1.5, more or less, long time ago, in this department where at the time Jean Biage was still alive and other people, good people, are still alive. And Wolfgang is a world-recognized specialist in lattice gauge field theories and has a lot of important contributions in this subject. And he will give us a short course of 4 lectures on Wednesdays and Fridays, I suppose.
This week at least. For the next week we have to ask Kanaya.
Yeah. Next week I will try to move the Wednesday class at least, because it will not be possible for me to stay here to attend your lecture.
Okay.
But you are most welcome, Wolfgang. And on Friday I'll be here.
Thank you. Thank you very much. Okay, thank you for coming despite the bus strike and everything. So this will be a kind of introductory overview without technical details, but just want to make clear what does the method consist of, what is the basic idea, and what do we do in practice. And I have, if somebody is really getting interested, I have both problems to solve, conceptual, theoretical ones, and also suggestions to carry out small simulations of toy model. Then one really gets familiar with the techniques. So the first lecture is, okay, I wanted to introduce path integrals. So I don't know, this is usually not taught in the quantum mechanics courses, so I suppose that people know, of course, the canonical formalism of operators, but I introduced the path integrals. Possibly everybody knows that already, but still, even in the first lecture, I will then also come to the question how this can be simulated and how one can obtain results, for instance, for a non-harmonic oscillator, which are non-perturbative, so directly at finite lambda, finite interaction parameter in general. That's what we want to see how this works in principle. A key element here is to work in a Euclidean space instead of a Minkowski signature. This can be justified by rigorous mathematics, which we will not go through, but we will make it plausible. And it does not only have a mathematical justification, but it has this Euclidean time has then a known physics interpretation in the framework of statistical mechanics. This should be this is very helpful because this gives us a handle how to address the problem with Monte Carlo simulations, and from them we can then link it also to spin models in statistical mechanics, which can be handled in the same way, and gives us it is good to have the both languages then talk about correlation lengths and so on to establish what means the continuum limit, what do we ultimately need. And once we have done all that, it is actually a small step, it becomes quite automatic to introduce also quantum field theory in the lattice regularization. This transition here is much smoother than in the canonical formulation. We can start with classical field theory, proceed to quantum field theory in the same way as here we proceed from classical to quantum mechanics. And then we start, of course, with the simplest case, scalar fields, then introduce gauge bosons, then fermions. That will keep us busy for a while, how to do this in the lattice regularization. And then we have actually all the concept for the lattice QCD formulation. I will not discuss in details the algorithm, how lattice QCD is simulated. We will see how simple models are simulated here. There are advanced complicated algorithms which are more for specialists, but we know in principle how it is done, and we look at some results and the status now in the 21st century. And once this is done, then as a kind of selected topic, I would like to discuss the particular issue of chiral symmetry. It's well known that chiral symmetry poses hierarchy problems, why there are actually light fermions, why there are, for instance, two quark flavors which are much lighter than the natural scale and QCD, the lambda QCD. If the mass has an additive renormalization, this does not seem to be something natural. Now, if we have chiral symmetry to refer to, then we can say there is no additive mass normalization, this is natural, but chiral symmetry first has to be implemented. And if we perform naive non-perturbative regularization, it will always slip away and renormalize again. So we have here a conceptual problem, and it is not easy to solve because we have another problem called fermion doubling. If we discretize a Dirac operator in the most obvious way, then there are always two copies of each fermions which are not ordered and which spoil the correct results. Oops. But we will show then a rather recent, it's a few years old only, solution to this problem, which is called the Ginzburg-Wilson relation, which at least for vector theories, which couple to left and right-handed fermions couple to gauge fields in the same way, this is a clear solution. If you deal with chiral gauge theories like the electroweak sector of a standard model, the problem is still not really solved. But at least for vector theories like QCD, then the problem can be solved in a way which is not particularly user-friendly to simulate, but at least it settles the question conceptually. Okay, so before actually starting, just a little bit of motivation in popular science terms. So the old question that we are concerned with is what the world consists of, and the Greeks already assumed there are some basic building blocks which they called atoms, but now we will call them elementary particles and antiparticles. First we have the fermions here, the leptons and the quarks, and part of the standard model, now also experimentally established, is the Higgs particle, which is then the only scalar among these particles. And one often says the interactions are transmitted by gauge bosons. This is not completely correct because the standard model at least contains also Yukawa couplings and then addition gravity. Of course, we will ignore gravity in this context because in particle physics it is usually negligible. The gauge bosons, here we have the photon, the weak gauge bosons, which are massive, and then 8 gluons, which transmit in particular the strong force between the quarks and between the among the gluons. So that they provide, for instance, the confinement of quarks, and what is mentioned massless, that there is also a confinement of the gluons themselves. But what we really perceive in our everyday world are not these quarks and gluons, but are hadrons, right? hadrons, in particular baryons, and the popular saying is that they consist of 3 quarks or mesons, which consist of a pair of a quark and an antiquark. Yeah, like a proton and a neutron, or like a pion. But this is, I wrote this purposely in inverted commas because I will show in the next slide that these statements are completely misguiding. One should call this valence quarks, and if you count the quantum numbers, then it's correct. But if you look at the mass, then you will see that this is completely wrong. If we consider, for instance, a proton, then the popular saying is this consists of a UUD quark and the neutron of a UDD. Now, if you look at the masses of these quarks, which are provided by the famous Higgs mechanism, they're in the range of 2 to 6 MeV, not more. So these 3 quarks together contribute maximally about 2% to the mass of a nucleon. So that means 98% are actually not due to the Higgs mechanism. 98% means of any macroscopic object that we have, like this laser pointer or any macroscopic object, is basically in the nuclear masses. And so most of the masses that we experience in our daily life has actually hardly anything, very little to do with the Higgs mechanism, in contrast to a lot of popular science articles and so on, which said now we know where the mass comes from, but actually it's only a small contribution to the mass of a macroscopic object. Of course, the mass of an electron, for instance, comes from the Higgs mechanism, but of a nucleon not. But then it is contained in some kind of foam of gluons and C quarks which emerge inside the nucleon. And there we can say, okay, there's a lot more inside going on, but it is very difficult to estimate how much addition there is, and if we really get to this 939 MeV, for instance, of a proton. And the question is then, is this number actually predicted? Is this consistent with the standard model? And the answer to this question is rather recent. So there we only about a few years ago we can say we can answer this and we can confirm this up to about 3% of uncertainty. Of course, the textbooks wrote since the 70s that UCD is the correct theory of strong interaction, but only now we have, and it works well in high energy experiments where the interaction is suppressed, but to really predict hadron masses from QCD, from first principles, this is only very recent, and only now, just now, we can really confirm that this is the correct formalism of strong interaction. Okay, so what I want to do here is, this is the overview of branches of physics. I want to start with classical point mechanics, you know, of course, and then from there I want to show the path how to get to quantum mechanics in the path integral formulation, which is a generalization which does not only take one path into account but all paths. And then the next step I do another generalization. Instead of taking here only a couple of degrees of freedom, I take an infinite number of degrees of freedom. This leads from the classical level, this is the classical level, to classical field theory. And if I then perform the same step as down here, I conclude not only specific field configurations, but all field configurations, and this will lead us to quantum field theory. Or we can also go this way, first to quantum mechanics, and then generalize quantum mechanics to an infinite number of degrees of freedom. It will lead us to the same quantum formulation of quantum field theory. So this direction generalizes the degrees of freedom from a few to infinite, and this from the classical level to the quantum level. So this is the general guideline of the scope that I want to follow. And of course we will proceed in giant steps. We will not discuss, for instance, Richard Barty's relativistic quantum mechanics. We will jump over, because if you go from mechanics to field theory, we get something relativistic automatically without any pains, and nor relativistic quantum mechanics and so on. And of course, it is sometimes good to look at the really basic aspects which can be overlooked if one studies a lot of details, as it is done in the regular lectures. So if we start from the most simple concept of classical mechanics. So we have a point particle, let's say, which has its coordinates, and the coordinates are then the degrees of freedom, and it may move in an external potential, say here according to Newton. Then we can if this is if the potential is given, we can integrate its motion. If we have the initial conditions and there may be problems but in practice, but in general we can just integrate this by proceeding in little steps in time and then follow the trajectory x of t of this particle. Now, if we want not only to proceed in infinitesimal steps but in finite time steps, then we also know what to do. Since the 18th century, we have to deal with the Lagrange function and consider their integral in time over an entire path of such a Lagrange function given here, which I will specify, and then the condition to find the classical trajectory is to look for a stationary path where the variation of this action, the integral over the Lagrangian vanishes, and this is equivalent to Newton's law in each moment of this trajectory. So what this means is, okay, the Lagrange function in the simplest form has this form, kinetic energy minus potential energy, and then at an extremum we can then look at the variation with respect to the coordinates and to the velocities, and here the endpoints are fixed, so we can shift this, we can perform an integration by parts, changes the sign, then we have this dx. This is arbitrary outside, so if the whole term must be 0, then this term here must be 0, and this corresponds exactly to the Newton equation in each moment. So we have here used this variational derivatives. This you can parameterize all possible paths in some way and then apply this to some of the parameters. Basically, the conclusion is that you have the same derivative rules as for ordinary functions, and the integration by path is without boundary terms if the endpoints are fixed. So what we do is we fix the endpoints, we look at all possible paths connecting these endpoints, and those which, if a path satisfies this condition, delta is 0, then at any moment it obeys Newton's equations. So that's what we can conclude from this, this bracket here being 0. Now, this stationary point in most situations is an action minimum. Exceptions can be constructed, but we stay with the usual case, and it is selected by the classical point particles. We see that there can be also ambiguities if there are several stationary points which we don't consider here, at least not in the beginning, and there can also be problems if the potentials are velocity dependent, but here we look at the simplest case, so we say, okay, we have a lot of possible paths. In general, this is a non-zero, okay, we're not reflected here. In general, delta S is non-zero, and then we find one where delta S is 0. So we can say, okay, there are a lot of universes possible, and delta S could be anything in each of the universes, and so this condition delta S 0 corresponds to a very specific universe, which is the one where we live. And here the people in the 18th century started to do a lot of philosophy around this property, and people like Leibniz and Maupertuis concluded that we live in kind of the best possible world because kind of a very good property that this variation is exactly 0, and they also concluded that this must be a proof for the existence of God because only he could do this optimization that delta S is exactly 0, and then this of course provoked objections by other philosophers like Voltaire, who was an atheist philosopher who wrote a long novel, Candide, just to ridicule this hypothesis of the best possible world. So his hero Candide believed strongly in this philosophy in the beginning, and then all his life he has bad luck, everything goes wrong until until he starts to doubt about this, and so at the end of his life then he is not so sure anymore if this is really the best possible world. So. But now the next step will be that we proceed to quantum mechanics, and there the principle of least action that we have seen here is actually not valid anymore. Of course, also Hamilton principle is not valid anymore, and therefore also the philosophical discussion does not apply anymore. So now we get to quantum mechanics. First, again, the scope is that we proceed from classical mechanics to quantum mechanics, and then in a second step from classical field theory to quantum field theory with the same procedure. This is the formulation in terms of path integral. And I assume, okay, you know the canonical formulation of quantized point mechanics. This is at this level, this is non-relativistic, and there are advantages and disadvantages in this formulation. An advantage is it's much more intuitive and transparent to get the connection between classical and quantum mechanics, and also to quantum field theory. A disadvantage is that a simple system like a hydrogen atom can hardly be solved in this framework, and this is probably the reason why it is not told in any lecture, basically in any introductory lecture of quantum mechanics anywhere in the world. In contrast, I mean, in the beginning, I think Feynman hoped that this will be the standard way to teach quantum mechanics, but it was not adopted in this way. So now we can, of course, proceed much more efficiently than Feynman, because we can assume already the canonical formalism, and then it's quite quick to derive the alternative formulation in terms of path integral. So we will use the Dirac notation, and we say, okay, first of all, canonical formalism, the state of a particle is described by what we call a ket, which is simply a vector in a Hilbert space. A Hilbert space is a vector space which has a scalar product. So this could then be the second factor in such a scalar product, and the first factor would be called its Hermitian conjugate, which is a bra, and so together this makes a bra ket. And if we use the same state of the particle at any time, this is normalized to be 1. So this is the basic formalism of quantum mechanics. Now, of course, we can introduce many bases of such a Hilbert space, for instance, the basis of position eigenstates, or the basis of momentum eigenstates, or of energy eigenstates, and there are eigenstates of a corresponding position operator, momentum operator, or Hamilton operator. So first of all, a basis is something complete, so if we sum over all these states and build this dyadic product, ket bra, then this is a matrix. And if we sum over all them or integrate over all of them, this must be unique. And the same in momentum space, where we need this, for conventional reason, this normalization factor. Or this is then Hilbert energy space. This can be a sum or an integral depending if the spectrum is continuous or discrete. I wrote here as an example a sum, but of course it will be the same. It also gives 1 at the end. And now we can construct a wave function if we take the scalar product of a position eigenstate with the vector that describes the particle with this ket, then we get a function of time and space. This is the wave function, which it's absolute square. This gives us the probability where the particle could be, or we can do the same with a momentum eigenstate. Then we get the wave function in the momentum space. Now we can also look at the transition from one space to the other. For instance, this is the wave function in position space, but we can look at this p psi. This would be the wave function in momentum space, and then we insert this xx and the integral. So all we do in addition is just inserting a factor 1. So that doesn't change anything. Then we know, okay, this is the position wave function, and this product is also known from canonical quantum mechanics. This is this exponential here. So we end up exactly with a Fourier transform, which takes us from the wave function in position space to momentum space, or vice versa if we change the sign in the exponent. We used only this property that we showed before, that this integral over this xx here is 1. And we can look at linear operators. Linear operator acting on such a vector in a Hilbert space would then be, if we want to let it act on a wave function, it would then first act on the vector, and then we take this scalar product, and we can look at it. If it is an eigenvector here, it is easy, but otherwise, if we take, let's say, the eigenvector of the wave function in momentum space is, of course, the momentum times this wave function. But if we apply it to the wave function in position space, then we have a problem because it's not in the same basis. So we first do this transformation, then here we have the object in momentum space, and we see that we get the same result if we apply this Aula operator with this prefactor. Then we get again this operator applied to this product, which is the wave function in momentum space, and so this is then what we have to do in position space to get the same result. So this is all the standard canonical formalism, and we also know how to look at time evolution. Time evolution is given by Schrödinger's equation. So this is the infinitesimal time evolution. In this sense, this is the analog of Newton's equation in classical mechanics, in the sense that it only gives an infinitesimal time evolution, and we multiply here by the Hamilton operator. And now we can ask, this is perhaps not so well known, could we do the same step as before, that we look at a finite time evolution, not at an infinitesimal one, but a finite one. So the question is, this was actually quantum mechanics in a Hamiltonian sense. Could we also do quantum mechanics in a Lagrangian sense? That's a question which is, in the usual quantum mechanics courses, they stop here. They do not really address this question. But of course, the answer is yes, we can, and this is what we want to illustrate now. So first of all, this vector can be transformed to another vector at a later time. There must be a transformation for it, and this transformation I call the evolution operator. So far, this is only an ansatz. So far, this is only a notation. We haven't gained anything yet. But now we want to make sense of this, and let's say proceed in the same step as before from Newton to Lagrange formalism. And now we look at the wave function at a later time in any position, starting from the wave function at an early time at any position. So here we have here the psi t. This is now here the psi t. We multiply with this u, and then we take this x prime to get this formulation, and we plug in again a factor 1. So if you skip the factor 1, it's exactly what we have up there with this x prime of this here, and we only insert here the factor 1. But once we do this, we see here we have a different interpretation for this term. This is the wave function at an earlier time at any position, and then we have the integral. This we can take out, and then there is this factor left here, and this is called the propagator. So all the rest is completely generic, but if we want to discuss a particular system, its characteristic is exactly this propagator. So the matrix element of this evolution operator, so if we know this, then we know what the system behaves like. So this is the challenge with the central object to deal with. Now if we apply Schrödinger's equation at time t prime, so this is easy to see here, then we get again this factor, the Hamiltonian operator, so we can write a Schrödinger equation for the evolution operator, so which is given here. Now it is the time evolution is then shifted to the evolution operator, not to the wave function anymore, but then it corresponds exactly to Schrödinger's equation. And if we have the privilege that the Hamiltonian operator does not depend explicitly on time, then it is trivial to integrate this by just putting this up to the exponent. This is the obvious solution here with the boundary condition that u of t is of course 1, because there is no evolution which is obeyed here. Now, if we do not have this privilege, then it's getting more complicated. Does anybody remember what one has to do in this case? If h is time dependent.
You need to integrate the time on temporal.
Yes. Yes, there is a name for that.
Dyson series.
Dyson series, exactly. Yes, Dyson series. Then each term has if we do the expansion, each term has one more integral, and then there is a sequence for the 10th term. We have a sequence of 10 integrals. So it's something very tedious to do. It is basically a perturbative expansion, but here we stay with the simplest case where we simply have this exponent. And now we can look at, first of all, I claim that this propagator contains information about the energy spectrum. This is Something very important if you want to, for instance, compute a biomass or proton mass, it's basically the energy spectrum. And just to illustrate why this is important, let us look at the propagator with the same initial and end state, xx here. Then we plug in here this exponential, and so this Hamiltonian does not apply to this basis, so we insert here another factor 1 with this sum over n. Then we can apply the h to the end, and it's the energy state, eigenstate En, given here. And now this is a pure number, no more operator, so we have simply xn nx, so that's the same thing, absolute value squared, and we are left with this exponential here. So if we know the behavior of this propagator between the same beginning and end state, we know its behavior, then we can extract in principle the energy eigenvalues. How to know that, this will be discussed later, but just by some miracle we know this quantity here, and we see how it behaves. If we separate t and t prime, then we can extract the energy eigenvalues. So this is something to be kept in mind. Now, in the transition of x to tx to t prime x prime, we can again insert a unit operator at some intermediate. Okay. We can also insert some unit operator at some intermediate time and use this decomposition. Right? We go from t to t1. T1 is somewhere between t and t prime, and from t1 to t. So this product of two, we can certainly split the evolution operator into the product of two evolution operators in this way. So first we do that, we have this u of t to t1 and t1 to t prime, and then at this intermediate time we also insert a factor 1 by integrating over all position eigenstates x1, and this way we have actually the product over two propagators with this integral here. So in pictures this means we propagate from this beginning and end states are fixed, but we propagate from here to some position eigenstate x1, and then from there to the end state x prime. But we do not know which one is x1, so we integrate over all possible x1s. So this must be an equivalent formulation for the propagator. And this can be viewed like the two-slit experiments, where we say, okay, we do not know where the beam passes, so we have to sum or build a coherent sum over the two possibilities. Now we don't even have a wall, so we simply sum over all possibilities. So this is the integral here. But now we say, why do we have to take particularly this time t1? We can take another time. Here also we don't have a wall. We can repeat this many times, and if we do this systematically, let's say we split it into small intervals delta, which is the whole interval divided by n, and after each delta we do the same process. So then we would have propagators. We go from here to the first x1, here x2, x3, and so on, and each time we have to integrate over all possibilities where the particle can be. So then we have a set of such skeleton paths which connect, which always proceed by a little time step, will later be infinitesimal delta, and goes from here to there, but we actually sum over all possible paths here. So how to write this mathematically? So we have to integrate first over all these intermediate position eigenstates, x1 to xn minus 1, xn is the x prime, and then we go from x to x1, from x1 to x2, and so on, and we have each time an evolution operator which just provides a small evolution. What is the advantage by limiting it to small evolutions? We will see in a moment. Roughly speaking, this is what gives us the connection to Schrödinger's equation, where we can then use the results of the canonical formalism to evaluate such one of these elements, and once we have such a prototype, then we know all of them. So we have to sum over these trajectories between the endpoints. And okay, again, we have to we want to compute one of these prototypes, an xi to xi plus 1. If we know this, then we can build here the product, and we get then an expression for the entire for the entire propagator here. So let us concentrate on one such transition over a very short time period. So this we do now in one dimension. For simplicity, adding more dimensions is trivial. It's just a matter of just changing the notation. And I assume also a simple form, the standard form of a Hamilton operator, given here, kinetic plus potential energy, and this is the time step Ti plus 1 minus Ti. So this is the element that we want to look at. Now I write the evolution operator here with the Hamiltonian. I plug this in, and T, this time difference is this delta. So here I insert what I assume in the line above. And now the problem is that I assume the potential depends on x, so I could apply it here. But the momentum does not. And now they are both in the exponent. So here we have a problem, that they are both in the same exponent. And of course, life would be much easier if we could separate them and write one exponent for the kinetic term and the other exponent for the potential term. Now the question, if we can do that, then we can proceed. But the question is if this is justified. And first of all, we can say if these operators are bounded, then we can certainly do that in the limits of very small delta. This is, I believe, the small delta. Then we can certainly split it in this way and say the extra terms here depend on some commutators between A and B, some operators, and but they come with order epsilon square. However, for realistic problems in physics, these terms do not need to be bounded. They tend to be bounded from below. The kinetic energy is bounded from 0 if the particle is in rest. The potential energy should be bounded from below, otherwise we have an unstable situation where the particle decays to some minus infinity in energy. So the realistic situation is that it is only semi-bounded. And in this case, it is not obvious at all if this factorization of the exponents, which is called Baker-Campbell-Hausdorff formula, if we evaluate this term, also proto product, if this applies. But the mathematicians have worked out that the semi-bounded condition is sufficient for this to apply. So this we will not prove here, is subtle mathematics, but it is very useful to apply this factorization for assuming that B and B squared are semi-bounded. Once we can do that, we can go on. And okay, there's one of these, I have a homework where one elaborates this property for an example. So that's something to keep in mind, that this step is not trivial at all. This is actually, there is subtle mathematics behind. But once we accept this, and we now look at infinitesimal delta, so we can skip this delta square, then we have a separation of this kinetic and the potential exponential, and now we can proceed. We can apply this to the end state and insert a unit operator within momentum space here, Vp, and the integral over p. And once we have done that, then we can apply the p squared to that one. We get simply the eigenvalue and the x to this here, and then we are left with an xip and p x1 plus I, and this is the exponential that we had before. So now everything seems to be clear, but there are still, so okay, we have used this property that this is an eigenstate and this too that we had before, but there are still some subtleties to be considered. First of all, in this term, it is actually not so clear if we should write xi or xi plus 1. Because I could write it once there are, I could write this factor also on the other side. Once I believe in the factorization, then it applies to xi plus 1. Now, which is the correct argument here? And the answer is, for this Hamiltonian, it doesn't matter, because the difference is for a smooth potential is again of order delta square. But it can well matter if we have, for instance, a potential which also contains derivative, like such a vector potential. Then actually the difference does matter, and then we have to make a choice. And this is not surprising because the operator formalism has the same problem. If we start with such a product, x times p, then we put operators, we also have an ordering problem. We don't know which order to take, and the rule is to take a symmetric order, so half time the anticommutator, and the analog rule here is called the midpoint rule. So in that situation we will take the midpoint between xi and xy as well. But again, for the simple Hamiltonian that we have here, it doesn't matter, so let us just stay with this xi. Then the next step is that we have an integral over momentum space, which looks like a Gaussian integral with this factor, but there is a problem with it that we have this I in the exponent. So actually it is not a Gaussian, it does not even drop to zero at infinite momentum. Otherwise, I mean, we can absorb this linear factor, of course, but the question is how to handle this. And this is sometimes called the funny Gauss integral or so. We can, a simple explanation what we do is if we replace delta, the time step, if we added a tiny negative imaginary part, then it turns into a Gauss integral. We can do the integral and then let the epsilon to zero. If we do that, then, okay, so here you see then this has a negative real part in the exponent. We can do the Gauss integral and afterwards let epsilon to zero. If you don't trust this argument, actually I can understand, because if you take the other sign of epsilon, it doesn't work at all, and then it's a bit a dangerous argument. But I have now also in this set of homework, I have a homework to show this with Cauchy integrals exactly that one gets, we get the result which corresponds to a Gauss integral, just ignoring that there is the factor of I. You get exactly the same as if it was a negative real part. So this is a part of the homework to justify this exactly with a Gauss integral. We have to take a detour, not integrating along the real axis. We can go around and then show that this is actually the exact result. So if we do this and treat it like an ordinary Gauss integral, okay, we see what happens. We first absorb this linear term, and then we are left here with this difference. If we complete the squares, and then this is all standard procedure, and then we can do the Gauss integral. So we are left with this square here. The potential doesn't change, and so this is all what is left after performing the integral over the momentum. And okay, yeah, this is what I mentioned already, that one can justify this rigorously with Cauchy's theorems about integrations in the complex plane. And okay, so now we have a result for one of these transitions, and now all we do is insert this each time for each of these factors that we have. We have many of these factors, right? Here they are, we have many of these factors. We insert this result each time, and then we get this sum in the exponent of these differences squared. And here this is what I write symbolically as the dx, which incorporates all the integrals over this midpoint, this intermediate points, and we are left with this minus v here. And now we can take the limit delta to 0, and then this corresponds exactly to a derivative. So this is the well-known kinetic term, and what we have here in the curly bracket is, of course, this is known as in the curly brackets, this is the Lagrangian. Yes, and if we perform the integral, then it is the action. So we have this prefactor I divided by h bar times the action. And then we still have to worry about this dx. This I will come back later, but let's postpone that. Again, the generalization to higher dimensions, such as 3 dimensions, is completely trivial. You just have to write vectors every time instead of one coordinate. And then we have the famous celebrated path integral formula that the propagator from x x to x prime is this, the integral over all possible paths, where each path is weighted with such an exponential factor I divided by h bar times the action of each path. So okay, what is still not done, this is the main problem, is then to deal with this, we call it the functional measure, the measure over all possible, integrating over all possible paths, which has the set has a very high degree of infinity. This we suspend for the moment, we will come back to that of course, but just to discuss a little bit what this means. Okay, so first, this is the measure. So we have here this prefactor for each of this, okay, this is now in 3 dimensions, and for each time we do such a Gauss integral, we get such a prefactor, and then we get all these integrals. If we let delta to 0, this prefactor is highly divergent, because first of all here this goes to infinity, and n is the number of intervals we have, this also goes to infinity, so this is highly divergent, but we will see in a moment that this doesn't bother us so much, because in all physical quantities this term cancels. What bothers us is that we still have to perform all these integrals. But what we are doing is we are intuitively speaking, integrating over all possible paths, connecting these initial points and in world space, world point and end point here. It is non-relativistic, so these paths are not even restricted to the light cone, so really a summing over absolutely everything. And actually this is similar to what you know from optics. In optics, in the beginning, you were taught the Fermat principle, that a beam connects, takes the shortest, the fastest connection between endpoints, but then we have a refined version, which is Huygens principle, and says, well, it propagates in all directions, and everywhere where it passes, it emits a new wave. Basically, this is actually the same, and this is doing quantum mechanics, or mechanics, say, in the spirit of Huygens principles. Just people didn't have before the 20th century to apply Huygens principles to mechanics. And now if we sum over all these paths, they are not all weighted equally, but they have this exponential factor here. Each path is weighted with such an exponential factor here. Now if we vary the path a little bit, that means that this exponential will in general rotate very rapidly because h bar is so small. So if this varies a little bit, it varies maybe 1,000 times h bar. It runs through a lot of rotations, so we know that there will be a lot of cancellations going on. And the exception where there is not so much cancellation going on, what is the condition for finding such an exception? Cancellation is not so bad with one path and its neighboring paths. If you have a stationary path, so if you say the variation is 0, then the neighboring, okay, so usually you have such a path, and if you vary it a little bit, then the S varies a lot and it rotates like mad, and most of the contributions cancel. But if delta S is 0, then the neighboring paths are basically in phase. So in first approximation they give the same phase, so we have a constructive interference. They amplify and do not cancel, at least in the first approximation. So this will give us the main contribution. And now we see the link to the classical mechanics that we had before. So the exception there is this vicinity of a stationary path where delta S is 0, usually the minimum of the action. There we have a covariant sum, and the amount of cancellation depends on this h bar, and the limit of h bar to 0, the dominance of this classical path would be complete, and the rest is completely negligible. So then we are back in the classical limit. So only now we understand how this property of the best of the possible world comes about. Actually, it is not one world which selects this delta S 0. Actually, all paths are there, but since the h bar is so small, the vicinity of this delta S 0 path dominates over the rest. So that gives us a new interpretation without this strange philosophy behind. But of course, we also know that in the real world, h bar is not 0. it contributes a little. That means also the rest of the paths contribute a little, and these are exactly then the quantum effects. So this makes then the difference between classical mechanics and quantum mechanics. So all in all, we have now an alternative formulation of quantum mechanics, alternative to the canonical formulation. It is in the spirit of a Lagrangian, and then the action appears not of the Hamiltonian form. It is more intuitive in the sense that we say, oh, okay, we sum over all paths and then we build a coherent sum, and h bar could be varied between 0 and its value nature or higher, and we have an interpretation for that. At least to me this seems more intuitive than a rule like taking Poisson brackets and replacing it by a commutator or something like that. Here I find this much more intuitive. We have no momenta, instead we deal with velocities. This is simply a consequence of Lagrangian instead of Hamiltonian formulation. But what is more important is we have no more operators. In this process of evaluating this transition element, we have eliminated all operators. We are only dealing with coordinates. And this gives us the first link. This formulation is much more computer friendly because operators are some kind of a tedious object, or coordinates is what the computer immediately knows what to deal with. So this is very convenient. No more operators, only coordinates. But on the downside, we have this tedious functional measure. We have to actually an infinite number of integrals to deal with. So we will have to discuss what to do about that. So that's certainly the disadvantage of this formulation. So this is the overview to start with. I don't know, are there comments already at this point? Or?
That depends strongly on the value of each bar.
Yes, how strong this interference is, and but this is natural because the quantum effects should depend on the value of h bar. So if you imagine a world where h bar is 100,000 times larger, then you expect much stronger quantum effects, and this comes out correctly, yeah? Because then the cancellation is not so strong anymore, and then we have more contribution even from paths far away from the classical one. Yes, so this is
the quantum problem.
Constant value. When yh bar has this exact value, this we cannot answer. Yeah, I think here we are in the same position as canonical quantum mechanics. H bar is given by observation. We cannot really say why it has this particular value. Well, if somebody claims that he can derive that, I do not really trust it. Because, okay, let's say the speed of light also, these natural constants, you can say, okay, it is natural that they exist as constants, but why they have the particular values that we find in nature, I don't think that there is a good explanation for that. And then you can ask the question, if you change it, is this still a possible world, or does it lead to some inconsistency? Here we would say it is another possible world, we would say with different quantum effects. But okay, if you take the whole quantum field theory and so on, then if this would lead to some inconsistency, maybe that's hard to say. Okay, this would be beyond scope to answer it. But it's a good point there too. Okay, now all this was in the usual Minkowski matrix with real time, and the next step is to proceed to Euclidean time. So we have already used a little bit of an imaginary component of the time when we replaced, maybe you remember that this delta by delta minus I epsilon, then this was to justify the Gauss interval. Now, okay, we already dealt in some sense with a little bit with complex time, and now we do this more radically. We say we simply replace the time by an imaginary time. We call this Euclidean time. This substitution here is also known as a Wick rotation, because in the complex plane this factor minus I corresponds to a rotation, and it clearly transforms the matrix of a Minkowski space into a matrix of Euclidean space, where now all coordinates and time have the same signature in the matrix. So this sounds like a daring, dangerous step, and certainly if you look at the dynamics of some process, it would change things completely, and we'll come back to that. But if we look at expectation values, as we will see later in field theory, actually this transformation can be justified. It does not really change the results under some mild assumptions, which are known as also the Schrader axioms. We will not go through them because this is deep mathematics, but we can say in practical life, in general, we don't need to worry about them. For all reasonable approaches, they are satisfied, and at least in some limit, which then justifies the substitution. So now we want to work simply in this Euclidean space instead of the Minkowski space. And not only that this can be justified, as I mentioned in the introduction, the weak-rotated quantum mechanics also has a known physics interpretation, and this will give us a link to statistical physics. So first, as an example, let us look at Schrödinger's equation. So this is the simplest case, let's say no mass and mass 1, and simply this is the kinetic term and the Hamiltonian. And with h bar is at 1 here, and the mass is actually 0. And if we replace this by a derivative without the factor I, then this turns into a diffusion equation or heat equation, which is of course not reversible anymore, so it's a completely different equation, but it also has some interpretation in physics. This is given then by random walk dynamics, where this is the probability where the particle could be. Just to show that after this transformation we still have an interpretation of the system. And now we come to the link to statistical mechanics, to the formalism. And statistical mechanics, basically everything depends on one quantity and its reaction to change of parameters and so on, which is called the partition function. Partition function is actually just a number, but the way how it reacts if we change a parameter, so if we take partial derivatives of it and so on, this gives us the whole of statistical mechanics. So the partition function is the trace over e to the minus beta, where beta is the inverse temperature. I set this Boltzmann constant, I set to 1. I can simply take the temperature in units such that this is 1 and times the Hamiltonian. Now I can write this trace, of course, in any base of the Hamiltonian of the Hilbert space that we are dealing with. And for instance, I do this now in the base of position eigenstates given here. This is one possibility to write this trace. And now the next step is that this exponential here is actually of the form of an evolution operator if I assume this time difference here to be imaginary. So if I replace beta by this, then we see that what we have here is actually an evolution operator, and the whole object here is actually a propagator with these closed boundaries x to x, and then we simply integrate over x, so this is closely related to what we had before. And so this corresponds to a propagation in Euclidean time over duration, which corresponds to the inverse temperature with periodic boundary conditions between the initial and final state are the same. And now we could do exactly the same as before. I will not repeat everything. In this case it is even simpler. So we divide then now beta, this duration, into infinitesimal time steps. This is n times delta divided by this h bar. Insert one operators each time for to do this. Okay, we separate kinetic and potential energy, insert this one, and here the integral is now really just Gaussian, because we are dealing with this imaginary time, then this is really straight Gaussian. So in this sense it is much easier than before, and we end up with this term, a functional integral expression for the partition function. Where this quantity here, first is a functional of each path, and I call this now the Euclidean action. Euclidean action will be described here. First of all, okay, we get it in this limit delta to 0, where delta is this difference squared and so on. This is what we had before. Now we have this factor I in front, if we come from the Minkowski space, and if we attach the minus I to this dt, then we get here a minus. So this turns into minus the potential. And in the kinetic term, we have this derivative squared of the time. So if we make time imaginary, this gives another minus. So the difference is that now kinetic and potential terms are additive. So we have kinetic plus potential terms, look like the total energy, but it's not given in momentum, but with velocities. And they are additive here, and most importantly, we have here a minus and not this factor I anymore. So now it is obvious that the minimum of the Euclidean action gives the main contribution, and paths far away from the minimum will be, their contributions will be exponentially suppressed. So this and the convergence will now be much better than before. We do not need this cancellation mechanism of the rotating phase anymore. We can simply rely on exponential suppression. So that is very helpful for practical purposes. So this shows why to deal with these quantities in practice, Euclidean signature is strongly favored over the Minkowski signature. So here we have again these integrals. Actually, before we had x1 to xn minus 1, and now we also sample, we have this trace which is xx, so we also have actually one integral more, but okay, the number goes to infinite anyhow, and this is the prefactor now with n of these integrals in 3 dimensions, so this is now the functional measure to deal with. Right, this xn is the same as x0, or what we call x and x prime, and due to the trace given here, so this trace here is then one more integral. That's why we have not only the intermediate points, but also integrate over the endpoints, in this case with the condition that the endpoints are the same. And now we can continue by referring to the statistical physics mechanism, formulation to introduce expectation values of some operators, let's say, some operators that represent a physical observable. Usually we would say expectation value is you take the trace, plug it in here. It depends on, say, some coordinates. In this case could also depend on other things, but here let's say only depends on the coordinates. Take the trace with this together and normalize this by dividing by the partition function, so that would be the term without if this was 1. So if this is 1, then the expectation value is 1 by normalization, and how this affects this trace, this is basically then the expectation value. This gives us the observables that we want to deal with. And now it is straightforward to rewrite this in functional integral formulation. We divide again by the partition function, and we take the functional integral where now this function of x is given here, and we have here the e to the minus Euclidean action. And now what we mentioned before, this dx has this highly divergent prefactor here, which if n goes to infinity or delta to 0, is highly divergent. But actually this is not much of a problem because it's the same in here and in here, so this always cancels. So this divergency does not really bother us because it never affects the expectation value of some observable. But still we have to deal of course with all these integrals. Yeah? But despite this divergent factor here, we have a ratio where the divergency cancels, so this quantity can very well be finite. And another remark is that actually I did not specify at which time point I take this x, and I will say now it can actually be taken at any time, because with periodic boundary condition we have translation invariance in Euclidean time. To show that, we go to Heisenberg pictures, we move this in time, let's say, according to Heisenberg, and here we have the minus s, so this shifted by time, but since we are under the trace, we can take this factor to the end, and all the exponents are with the Hamiltonian, so we can contract them, so this cancels against that one, it commutes with here, and then we are back with the formulation we had here. So the time does not need to be specified here. Now we take the limits that which would correspond to a low temperature or large beta. Formally call it infinite, but it's not quite not really infinite, it's just large to suppress subleading effects. And first look at the ground state of the vacuum, which then contributes, this is quite analogous to the classical graph in point mechanics, that we have then the dominant contribution of the ground state to statistical mechanics. So if the Hamiltonian is divided into its energy spectrum, we would say then only the E0 would survive. If we have here E1, E2, which are higher, they are more strongly suppressed if beta goes to infinite. So let's neglect the rest to start with. And if we insert this for the expectation value, we can simply reduce this to the e to minus E naught, and this as well, and we are left, in this case, we are left actually just with the ground states, which the operator being sandwiched between the ground states. So this is what we would call the vacuum expectation value. Now, of course, in real life, we want also finite temperature, which corresponds to finite h bar, and that activates, you can call it the terminal fluctuations, or also the quantum fluctuations, and we have to include that as well. And the difference is, so these are quite analogous mathematically. The difference is, of course, that in nature temperature can really be varied, whereas h bar is fixed. Yeah? But mathematically, they play practically the same role. So what we are often interested in is this object called correlation function, or two-point function, or correlator. Now we deal with two such observables, which are given now at functions of x at different times, and we want to know how they affect each other. And now the situation is different than if we have only one factor. So this is first of all the functional integral formula expression. This is the Heisenberg type operator expression. And now we see the trick before by moving this to the other side and then cancelling does not work anymore because there is another operator here. So here this separation between the t matters in this case. So here it matters how far they are separated, x of 0 and x of t. Now we can write this, say, in the energy basis to this trace here with this. These are the energy eigenstates. And so we can insert now this Hamilton operator. Here we have a problem because here we have another operator in between. So to start with, we can have here this En applied here, t minus beta. But then to apply also these Hamiltonians to some eigenstates, we need to do another sum. Here we insert the factor 1, summing over this n. Then we have e to the minus n in addition. And now if we take it together and rewrite also the partition function in this way, this is simply the partition function written in the energy states. We have then this matrix element times this. This is the absolute square, and here in the exponent we have this En minus En times t and this beta En. So now we see if we do again the same, that we make beta large, temperature small, so this selects the n equals 0 state. So we can also say we can reduce this to n to E0 and this to E0, but we are still left with the sum over n. So the situation is not as simple as before. So let us look how to continue. So okay, we have now the limit beta large. Then we have this m is put to 0, so we have this element here and this difference, but we still have the sum over n. And now what we can do is we assume also t to be large, smaller than beta, but still large, and then this reduces to what we call the correlation function. And if we take everything together, then we have a trivial contribution, as if the two operators would be completely independent. So if we subtract this contribution, we want to know how they are correlated, how they affect each other. So we subtract this contribution, we subtract the states where this would be NN or 0, 0, 1, 1. So the dominant contribution 0, 0 is cancelled here by this subtraction. This is then what is left, this is what we call the connected two-point function, and if we take t large, the next term that survives is a 1, 0 element, and then we have in the exponent e to the first energy gap to the minus the energy gap to the t. And this formula, this asymptotic formula, is known as Feynman-Cox formula, and this is very useful, again, if we know how such a connected correlation function depends at large time separation. How it decays exponentially with the Euclidean time, then we can extract the energy gap here. This energy gap is of major interest. Its inverse is called correlation function in statistical mechanics. But if we will do later, this is anticipating exactly the same in quantum field theory, and then this means this is the part at the mass of the lightest particle involved. Let's say E0 would be the vacuum, no particles, E1 would be the first excitation, one particle, so we get here the lightest particle involved. For instance, if we deal now with the action of QCD, and if we manage somehow to connect such a correlation function where the O is some pseudoscalar density, then we get from this exponential decay here, we can extract, let's say, the mass of the pion in this case. That's exactly the technique, try to identify such correlation functions, see how they decay with Euclidean time, and from the coefficient in the decay, we get the particles, the particle masses. That is the basic concept, and it seems easy here, but in fact it's not easy to get this, let's say, a pion mass from QCD in any other way. So that's the way to try to solve this and observe the decay, and from that we can extract the particle masses. Now we have so far only introduced the formalism. We have not really discussed how we can really compute path integrals. Now what are the prospects to compute them? Because this infinite number of integrals that we wrote is still somehow symbolic. We have to see how to make practical sense of them. And to really evaluate observables, as I mentioned before, or such a mass gap, E0 minus E1. First of all, we have here also, if somebody's interested, the case of a free particle can be done easily. The case of a harmonic oscillator can still be done because the potential here is quadratic. Then all the Gaussian, the integrals that we have to do, okay, they are of Gaussian type, and we can carry out one of them and then proceed by iteration and carry out an infinite and sum up an infinite number of them. So this is doable, this is the first thing that people did, and the results coincide exactly with canonical quantum mechanics. For instance, we can then extract the energy spectrum of the harmonic oscillator, which is probably the most famous result from quantum mechanics. We can get here exact coincidence, and the people trust in general that the two formalisms are identical in completely general situations. Although I think it's hard to really prove that, let's say, if we deal with curved spaces and so on, but in general, at least we do not have a counterexample to that. But the problem, a downside of this formalism is that analytic solutions are basically limited to the harmonic oscillator and variance that you can get by substitution from it. But if we do not have a quadratic potential anymore, so if we have higher terms is what I would call interaction, or a different type of potential, then we cannot do this, we cannot carry out these integrals analytically anymore. And the frightening case is the hydrogen atom with this Coulomb potential. This is a real nightmare. General opinion for a long time has been that this cannot be solved with path integrals. In Berlin, there's this Professor Kleinwood who has written a long textbook about path integrals where he claims to give the first solution of this and finds the right result, but they are very involve complicated transformations inside, and there are rumors that actually he has been cheating a little by using a result which comes from the other formalism in some well-hidden place. So I'm not so sure if this really works out, but in any case, even if it's doable, it's very complicated, and this is probably why lecturers of quantum mechanics 1 do not like this formalism, because they cannot show the spectrum of the hydrogen atom. But still we carry on with this now, and let us look now at the case of an anharmonic oscillator. So that would be the harmonic oscillator. Now we have, so far everything is quadratic. This splits into an xi plus 1 minus xi divided by delta, so these are all quadratic integrals. But now we add such a quartic term, x to the 4 term, and this is not Gaussian anymore, and here we have then a serious problem. First of all, this cannot be solved completely, not by canonical formulation, nor by path integrals, so we are in the same situation. What one could do is apply perturbation theory. This is the standard tool how to apply it, how to compute something approximately if you cannot do it exactly. So what perturbation theory does is we leave in the exponent the part that we can integrate, so which is quadratic, Gaussian, and the rest is then, okay, the x to the 4 term is then expanded here. The exponential of that is expanded here as a Taylor series. So that would be the first term, and then we can go on and so on. So these terms here, the correction terms, can be computed. Actually, if you go to high orders, it's getting quite tedious to do so, but in principle it's doable. But the first problem is that the convergence radius in this lambda is actually 0. So of course, if lambda would be negative, then the integral, so it's clear here, if lambda has to be positive. If lambda would be negative, then the integral is not convergent anymore. So we know actually the convergence radius around 0 is 0. So we don't even know if we can trust it if we if we insert a small lambda. And for some reason it works nevertheless if lambda is really tiny, although rigorous mathematically there is no reason for it. But now I did such an experiment some time ago. I looked at this ratio, second energy gap, E2 minus E0 divided by the first energy gap, so this gives a bare number, and this is kind of the interaction parameter. Lambda by m to the 3, this is also dimensionless, so I can write pure numbers on the axis. If I go with lambda to 0, here I have the harmonic oscillator, and then we know this ratio must be 2. If we switch on lambda, I know by some reason, it's my secret, how I know that this is the exact solution. And now I apply this perturbation theory, and the first order which gives us this term here, okay, is the tangent, it seems correct. The second order, this one, the blue line here, the third order, green, the fourth, this one. We see that the range that it follows, the black line, is extended each time a little. So this is qualitatively okay. However, this range is really small. So it goes about up to 0.02 of this interaction parameter. If you think, okay, I have solved it to fourth order and I take 0.1 for this interaction parameter, inserted here, I get a result down there which is completely wrong. So perturbation theory is, can very well be limited in its range of application to a very small, to tiny interactions, as we see in this case. And if you're just anticipating again quantum field theory, if there's a very similar model called the lambda phi to the 4 model, which has been computed in perturbatively up to lambda to the 5. This was only possible with sophisticated computer algebra because there are millions of terms to be summed up. And then you can see, well, if you translate it into this, you see actually that the range where you can trust it can well be very limited. And if you compare it to QCD, we have an interaction parameter alpha strong, and for some quantities QCD is solved to alpha strong to the 4, by far not to all quantities, because this is really tedious even with computer algebra. So this would actually correspond here to the fourth order curve, and we see that actually the applicability can well be limited. Okay, it's a different theory, I cannot transfer these numbers one by one, but we see it can very well be limited to very small range around the free case. So this is, perturbation theory is of course what dominates the textbooks, but I just want to illustrate here that it can very well be limited, its applicability can very well be limited to tiny interaction parameters. So that's why here we will address an alternative to evaluate this directly at finite lambda, leaving it in its exponent where it actually belongs without this perturbative function. Yeah.
How is calculated that solution?
Excuse me?
How is calculated is that solution for the general?
Aha. Yes. Well, there are different ways to do it. First, I will show you in a moment the numerical procedure by simulations, where you can do that, and we can calculate this to at least five digits of precision. In this case, actually, there is also an alternative. In this case, you can also deal with the Hamiltonian, and to solve it, you would need to diagonalize the Hamiltonian. Then you have the eigenstates. And of course, it is not diagonal, but you can apply a sequence of transformations which approximate their diagonalization better and better. And this is also numerical in some way, but different from the method I will show here. And then if you find a convergence in this iteration of getting closer to the diagonalization, then you can trust it. And this is actually, in this case, I must admit, it is more efficient. You can solve it to maybe 10 digits of accuracy. It's still not a precise solution, but to any precision that you're interested in. So this is, I've actually an office mate in Mexico who's working with such things, and he knows how to basically, if you could do the same in QCD, and I also know people who are interested, who try to do that, if you can also write a QCD Hamiltonian and try to diagonalize it, but with all these gluon fields inside and so on, it's getting an endless mess, and I think the people have been trying that for decades and made no progress with it so far. So in this case, I must admit the diagonalization of the Hamiltonian method works better, but in QCD, the approach has known basically is hopeless, so that's why we will look at an alternative.
Another question, this is similar to the beta function in quantum theory. This relation between the coupling constant and the different levels of energy. Or
to a beta function, I think this curve here does not correspond to any special function. You mean that the beta function, this like the gamma functions, this combination of the special function, the beta function?
No, the beta function of the renormalization group.
No, well, at this point this is quantum mechanics. So at this point the beta function, there is no renormalization of in this sense here. This will come later, yeah, this will come later. But okay, at least of course if I mention this example, then this takes us into all these problems. But actually, as long as we stay with quantum mechanics, beta function does not really.
Similar. That's what.
Of course, you can say. No, you see, I already put this in dimensionless terms. So if you do a simple scale transformation, they should not change. So you don't have this renormalization properties of field theory. So I think in this case it will not. Here you are right, of course, and here also will have better function properties. And for the harmonic oscillator, I think this renormalization does not set in yet. So that's okay. But this is you are right. If I mentioned quantum field theory, I should have mentioned that this is another difference. I should not. Okay, which comes in if you want to compare this here. This is good. Let's skip this point then. Now, just staying with the harmonic oscillator, I want to show you now the non-perturbative treatment, which is in the spirit of lattice simulations, how to evaluate this directly at finite lambda, and I will claim that this is possible numerically. In quantum mechanics, and later we'll see also in quantum field theory, and first of all we go back to a finite time step. Okay, still small but finite, then at least mathematically we know what we have. We have this half integral, it's an integral, okay, we have a time step of some finite length, and we divide it maybe in 1,000 sub-steps of short steps, but then we have 1,000 integrals, but at least it's something mathematically well defined. In the limit to the continuum, actually the definition is not clear at all. Even not only the question how to compute it, but even conceptually the definition is far from clear. The best thing we can do is to start with a finite time step delta, evaluate observables, and then do this at different deltas, and then extrapolate these observables to delta zero. That is the best thing we can do in general. Now, okay, just to illustrate that, so we would have let's say, some observable here, which is measured at some delta here, maybe with some error, and then we take different deltas, so that, and if we find a stable behavior with small errors, then we can extrapolate this up to some uncertainty, and then we say, okay, this is the continuum result. Sounds simple, but it is really defining it directly in the continuum, except for the harmonic oscillator case. There one has a rigorous formulation, this Wiener measure, but as soon as we have interactions, it actually even mathematically it is not clear what this functional integral means in continuum physics. Now what we do is we take the Euclidean action of one trajectory. So we take one of these trajectories. Okay, we have now fixed endpoints which are the same, initial point and endpoint are the same. So this is my x of t, and actually the t's are discrete, so it is actually a sequence of such points here, coordinates in t1, t2, etc. given here, and we compute we have a Euclidean action for that. We divide by the partition function, then it is normalized. And we say this is the probability, we interpret this as the probability for path x. X in square bracket is a path. So if we sum over all paths, then this is 1, so that satisfies the condition for probability. And of course, for this to be a probability, we have to require the Euclidean action to be really positive. Otherwise, if this is complex or negative or something, negative is not so bad, we can add an additive constant to make it positive as long as this is bounded from below, but if it becomes complex, then we will have a problem that we will mention below. This is what we mentioned before with the chemical potential, then we will have this problem that the probability interpretation doesn't work anymore. But let us assume that the Euclidean action is positive, really positive for any possible path. And now, then this gives us the probability, and now the method is that we tell the computer, we write a program which generates a large set of such discrete paths, again given by the coordinates at each discrete time, and which are closed, periodic, and they are random in the sense that there is some random involved, but these do not all have the same probability. The probability is given exactly the one given here. So that means those with low action have higher probability, but those with higher action can also occur, and they contribute a little statistically. So if we generate, let's say, 10,000 or 100,000, depending on computer summation of these paths, then we sum over them, and this gives us an approximation for the path integral. So first of all, we have then statistical errors, because the set of paths here is infinite, and we only take a finite subset. But if we take this probability, we implicitly reduce on both sides to the same finite subset. So the normalization works out, and then if you have 100,000 of these paths, we are left maybe with a statistical error as shown here, but this can well be, okay, if you have 100,000 paths, this is probably less than 1% or so, then okay, we can live with that. It is still not bad. If we need a smaller, then we can let it run and generate more of these paths until the error is small enough as we like it. So the error will always be there because we can never go through all the infinite number of paths, but it's not so bad. It's like if you want to know how much salt is in the ocean, you don't need to explore the whole ocean. 1 spoon of salt water is quite a good answer up to some statistical uncertainty to perform a measurement. And then we have these systematic errors. For instance, because we have this finite time step and we need then this extrapolation to delta 0. This, of course, we are not really simulating in the final limit that we are interested in, and also the volume has to be finite. Quite often we are then interested in infinite volume, so we need another extrapolation here. And in QCD, for instance, often people could not simulate at the pion mass where they wanted, so we need, in this case, 3 extrapolations. So there are various extrapolations necessary which bring in some